Yes, good morning, students. Let me move on. Okay, from where I left in the last class. Okay. So now today we will go for lens. Okay, then power. Then we'll go some MCQs today, right? Okay, now let's move on to lens. Okay, let's move on to lens. Lens is just any transparent medium. It should be an optically active medium, right? Lens is an optically active medium, or uh, lens should be such a medium it should have such a medium, it should allow that light to pass through it. Got my point? Is it right? So it should be a transparent medium, but condition is that the two surface bonded surface of that lens should be there must be two bonded surface. At least one bonded surface out of the two should be curved, right? Okay, now what is lens? Lens is a two surface, it's a transparent medium. It is a transparent medium with two surfaces at least one of which should be curved. At least one of it must be curved. At least one of it must be curved. Right or not? Actually, two kinds of lens we divide. One is diverging kind of lens and another is converging kind of lens. Two kinds of lens. So converging kind of lenses are called convex lenses. Diverging kind of lenses are called concave lenses. Converging kind of lenses, they converge the light towards the principal axis. Diverging, they diverge the refracted ray away from the principal axis. Okay, now one by one. Let us take now convex lens. Let me take first is convex lens. Convex lens. Right or not? Okay. Convex lens. Right? Okay. Convex lens. Done. So convex lens has got again two bonded surface. So what is the important thing here is, let me take here, this is the convex lens. Convex lens. Here there are two curved surface here. There are two curved surface. There are two radius of curvatures. So let the radius of curvature of this surface be R1. Radius of curvature of this surface be R1. So this is called a biconvex lens. We call it is what? Biconvex lens. If both radius of curvature, both radii of curvature are same, that is equiconvex. I mean, if in case both radii of curvature, if radius of curvature of this and this are same, then this is, we call it is what? Equiconvex lens. Equiconvex lens. Suppose one surface of this is plane and another surface is like that, bulged away out. So this is what we can say plano-convex. One surface is plane. What is the radius of curvature of this surface is infinity. The radius of curvature of the plane surface is infinity, and it has got some radius of curvature, let's say r. This is plano-convex. Plano-convex. We have got one more like concavo-convex, like that. So the radius of curvature of this is say R1 and then radius of curvature of this is say R2. But in this case, one surface, actually this surface is convex and this surface is concave, right or not? So one surface is convex here, both the surfaces are convex. Both the surface, one is here plane, another is convex. So here one surface is convex and another surface is concave. This is called concavo-convex. Concavo-convex. What do you call it is concavo-convex. Here you can look at here, radius of curvature of R1 convex surface is more. Radius of curvature of, okay or not? So what is more here? Radius of curvature of R1 is greater than radius of curvature of R2, right or not? So radius of curvature, who is more curved here? R1, let me take here reverse. Okay. So here more curved is what here? Let me take here, suppose like that. So it is more curved, no? This is more curved, and this is less curved. Less curved. It means say this is R2 and say this is R1. More curved is this, no? Therefore R1 will be less than R2. Radius of curvature of convex surface is less than radius of curvature of concave surface. This is called plano-convex lens. In all these lenses you could have observed here, the middle part is thicker than edge part. Have you observed it? Middle part is thicker than edge part. Middle part is thicker than edge part. Middle part is thicker than edge part. So when do you say convex? If the middle part is thicker than the edge part, then we could say it is a convex lens. Its ability to converge the light rays. What actually it does? It will converge the light. Even this concavo-convex are called meniscus also. Actually, these are all correcting lenses. For example, with these lenses, you are unable to fit the correct problem of the eye or correct lens you are unable to make. Then these will play a supporting role. These are all called meniscus also. So this concavo-convex lens is correcting lens also. They will here and there a small requirement is there. Then they will use this to fit the required things. Got my point? Okay, now. Okay, see here. Now in this here, middle is thicker than what is the point here? Middle is thicker than edge. Middle is thicker than edge. Got my? This is what convex lens. Got my point? It is a converging lens. It is a converging lens. Right or not? It's a converging lens, right? Okay, now so let me move on now. Another type, let me say concave lens. Concave. Another type of lens we have here, concave lens, right or not? Okay, now so concave lens is the middle is thinner. In the concave, what is here? This is middle part is thinner. This is a transparent medium. Here middle part is thinner. Say radius of curvature of this is R1 and this is R2. It is what we can say biconcave. Right? If both curvatures are equal, then it is equiconcave. If here also are, what you can say it is equiconcave. Right or not? If one surface is plane, its radius of curvature is infinity and its radius of curvature whatever may be r, it is called plano-concave. Right or not? So sometimes we have like that also. Like that. This is what, let us say this radius of curvature is R1 and this is R2. Here one surface is convex, this is a convex surface and this is a concave surface. It has got both, but here middle part is thinner than edge part. middle part is thinner, still it has got diverging effect. It is called convexo-concave. Convexo-concave. Still it's a diverging effect. It will show this is all correcting lens also, or simply meniscus also. Simply meniscus also. It is used to small changes if you need, if you are unable to fit our requirement with these will be used to correct the user, used to make our requirement. Got, these are all correcting lens also. Got my point? Okay, now. So let us move on now. This is called what? Which type of lens? They are diverging lenses. They are diverging lenses, right or not? Here middle is thinner than edge. Middle is thinner than edge. Got my point? Middle part is thinner than edge. Okay, now we'll go to the next concept here. Right? Okay, now. So here for lens, two radius of curvature is there, and at the same time for the lens we have two radius of curvature. Even for concave also we have two radius of curvature. So let us say this is R1. Radius of curvature of one is R1, and okay. This is a part of this circle. Its center is the first surface, say it is a second. First surface center is this C1. And in the same way, second surface center is what? Second surface center is somewhere here. Right or no? So the line joining between them and passing through on one more point, we call it is optic center. This is called, what is O here? Optic center. So line joining between C1, C2 and optic center, this line we call it is principal axis. What you can say? Principal axis. Right or not? Principal axis. Okay, now there are two radius of curvature. For one, this is the radius of curvature for one surface, and for second surface, this is the radius of curvature of first surface, and this is the radius of curvature of second surface. This is R2. Now what is the radius of curvature of first surface? Here to here. There. This is what you can say R1. Here to here. Here to here, radius of curvature of the first surface. Then here to here, here to here is R2. Okay or not? This is R2. What is R1? Here to here. This is R1. Got my point? There are two radius of curvatures for, and the same way for here also. This is one radius, it has got one radius of curvature, it has got another. So two center of curvature, two radius of curvature, for because two curved surfaces are there. So usually find two radius of curvature. Is it right? Okay, now let me move on now. Okay, there are two focus. One is first principal focus and another is second principal focus. We'll think of now what is first principal focus. Okay, if this is the lens, let us say this is a lens here. This is a principal axis. Which is first principal focus? If the rays, okay, if one point on the principal axis, say F1, so one point on the principal axis, say F1, if we keep object here, the ray going from this, after refraction they becomes parallel. They become the ray which is going here, okay or not? They become parallel. So this is called first principal focus. First focus point. Let us say it is also called first focus point. What you can say, this is first focus point. And the distance of this is optic center. What is optic center? It's a point in the lens where suppose what is optic center? Okay, let me define here optic center. It's a point in the lens. If any ray heading towards this point will never deviate, it will keep going forward. Any ray going towards this point on the lens, any ray heading towards this point on the lens, it will not deviate, it will keep going straight undeviatedly. That if ray going towards that particular point, if then that after refraction it never deviates, it will go straight. What is a optic center? It's a point inside the lens. Any ray heading towards that point will keep going straight without any deviation. Like here, ray is heading towards this, it will keep going straight. Then the point where inside the lens it is going on the principal axis. On the principal axis where it crosses that point, we call it is optic center. So this ray is heading towards a point and it is going straight. So one point is there, one hypothetical point on the principal axis. Any ray heading towards that point, okay, after refraction it will come out now without any deviation. It will go in the same direction of incident light. Got my point? This is an optic center. Okay, now what is the first principal focus? If we keep object at one point on the principal axis, after refraction, if the ray becomes parallel, after refraction, the ray becomes parallel, then the point where the object kept, that point, what we call it is first focus point. Okay or no? The distance of that point from the optic center, we call it is first focal length. What you can call it is first focal length. Done. In the same way for concave. Right or not? The ray, okay, let this be itself is, let me take principal axis. Somewhere it's a point here on other side of the lens. Okay, suppose the rays are converging to this point. If the rays are actually heading towards this point, if the rays are heading towards this point, after refraction they become parallel. After refraction they become parallel. The rays, the converging rays, they are heading towards one point on the other side of the lens in case of concave. So the point where they're supposed to go, then after refraction they finally become parallel. So this is called first focus point. What you call this point is what? First focus point. First focus point. You're getting my point? First focus point. This is a then the distance of that, this is the optic center. The distance of that first focus point from the optic center is called first focal length. What do you call it is? First focal length. First focal length. Got my point? Okay. Now, so let me move on. What is second principal focus? Second focal point. Second focal point. Same thing. Okay or not? Now see here. Second focal focus point. This is the lens. So rays which are parallel to principal axis. The rays which are parallel to principal axis. Right or not? So after refraction, they pass us through one point. After refraction, they pass us through one point. The rays which are parallel to each other, after refraction, they pass us through one point on the principal axis. Here in this case, the rays, incident rays are coming from infinite distance. After refraction through lens, where they meet it, that point we call it is second focus point. Second focus point. And the distance, this is optic center. The distance of that second focus point, focal length, we say it is f2. In the same way for concave, in the concave, condition here is that, what is the condition here? Incident ray after, okay, here incident rays, let me take parallel. Incident ray, let me take parallel. Here what will happen? After refraction, they diverge as if they appear to come from, they diverge as if they appear to come from one point. What is the condition here? Here also incident ray, here also incident ray parallel. If incident rays are parallel to principal axis as well as to each other, after refraction they appear to diverge from one point on the principal axis. This point we can say second focus point, and the distance of this optic center here, this distance we call it is f2, this distance we call it is f2. Okay, now in reality actual focal length of a given lens is second focal length only. Okay, when whichever problems and all, if at all they say focal length of lens, they mean second focal length only. Usually we deal with the rays which are coming from infinite, we take reference, and where they meet at. For convex lens, they they really meet at one point, then optic center to that point where they meet. Here references incident rays should be parallel, and wherever they meet at after the refraction, here they are really meeting and here they are appear to diverge from a point. Where they appear to diverge from which point they appear to diverge, that is second principal focus or second focus point, and the distance of that from the optic center is second focal length. This is a second focal length, and here this is second. Remember, if I say focal length of the lens, you should not take first focal length, you should take second focal length. So usually we go with second focal length itself is actual focal length of the lens. Second focal length itself is actual focal length of lens. Got my point? Now let me move on now. So briefly, anyhow you have learned sign conventions for concave mirror. Same will be there, slight changes. Let me move on now. Sign conventions, modern sign conventions. Same sign. I told you, sign conventions are needed to work out. Okay. Now let me take here sign conventions. Okay, for time being, let me take any optical device. It may be convex or concave. Let this say an optical device. It may be convex or concave. It may be convex or concave. This is a principal axis. Same thing. So always the object could be kept left side of the optical device. It may be convex lens or concave lens or any kind of lens maybe. Object should be kept at the left side of the optical device. So when this is, then incident ray will move from what? This is incident ray, will move from left to right. All the distance are measured here from optic center. All the distance are measured from optic center here. You know already optic center. Okay, for thin lens, this distance and this distance are negligible. So we measure from here only for thin lens. Okay, here to here distance are negligible, right? Okay, here usually what is convention says, all the distance are measured from optic center, I mean from this point, right? Okay, now distance measured against the incident light, opposite to incident light, that is taken negative distances. Distances measured in the direction of incident light, those will be taken positive distances. Height measured above the principal axis will be positive height. Height measured below the principal axis taken as negative. Simple. All are same, only what you have learnt in concave. So here instead of just their pole we have taken, here you should take optic center from where we are measuring all the distances. Got my point? Okay, this is regarding sign. Now tell me, the real focal length, real focus per lens is second principal focus. So real focal length of lens is second focal length. Now tell me, all the distance are measured from focus. Now focus to here optic center, all the distance are measured from optic center. Optic center to focus is this side. Incident light are this side. This is incident ray. So from optic center, this is the second focus. We are going from optic center to focus here in the direction of incident law. So focal length of convex lens we take negative. Here second principal focus is for concave is here, optic center is here. I am measuring here to here distance, that is focal length of concave against the incident light. This is incident light direction, it's coming from left to right. So I am measuring from optic center to focus from here right to left, that is this is focal length I am measuring from optic center to second principal focus. So for concave length. For convex lens, it should be focal length of convex lens is positive, and for concave is what? Concave is negative. Sorry, focal length of, okay, it is for concave, it will be what? Negative. Got my point? For focal length of convex will be positive and focal length of concave will be negative, as I already told you. Got my point? Real focal length is second focal length. So the distance from optic center you are measuring from left to right, distances are taken positive. From right to left, distances measurements are taken as negative. So focal length of concave is negative. Got my point? Done. Okay. Now let me move on. Okay, for what should be in the same way how I told you in case of concave mirror, here also same basics will run out. What is if the object is at infinity, image will be at f. Same thing, like object is at, all those things will be there. If object is at infinity, where will be image at? It will be at focus. If object is at 2f, image will also be at 2f. Hope these things you will be knowing it, right or not? So depending on the different object position, the image position also changes, right or not? Okay, now let me directly move on to power here. Power. What is the power of lens? Power of lens. What is the power of lens? It's a ability of lens to how much it has diverged the rays, how much it has converged the rays. If more it is diverging, then we can say power of that lens is more. For example, if this is the lens, let us say this is a principal axis and this is incident rays. Incident rays. With respect to this incident direction, one lens may diverge and one lens may converge the light rays and bring it here. One lens may converge here, and another lens may converge the rays here, right or not? So definitely here to here bending is more than here to here bending. Okay, this bending say 1 and this bending is 2. So which bending is more here? Bending 1 is more than bending 2, no? So for 1, the bending ability of lens is more. For 2, bending ability of light is less. So power for 1 lens is greater than power for 2 lens. Got my point? Power for 1 lens is greater than power for 2 lens, right? So how much more it is bending towards the, like if it is a converging lens with respect to incident ray, how much it has bent, how much it has converged towards the principal axis, then more it is converging, then we could say its power is more. Same way for concave also, it is diverging. Here it is converging, it is in case of concave it will be diverging with respect to incident direction, how much it has diverged the incident ray, more it is diverging, we could say power of that lens is more. What is the power here? So what could be power? It's a ability of that lens to converge or diverge the incident light ray. So I told you power of one lens is more than power of two lens. If power is more for one, then focal length is, focal length will be, you can say, f1 is less than what? F1 is less than f2. Power of one is more, but focal length of one is less. Got my point? Power of second is less, but focal length of second is more. Can you predict what here? More the converging effect, more the power, more the light ray will bend, but focal length will decrease. Got my point? Here the first lens is converging the ray in this direction and focus is this. Second lens is converging the ray and bringing here. So we have converged more, we have deviated more. So first lens is deviated more. So first lens is deviated more means focal length is less here. Then what could be the answer for this? So power is inversely proportional to focal length. Power is inversely proportional to focal length. More the power of lens, less the focal length of lens. Got my point? Okay, in the same way, so what should be unit? SI unit of this power is diopter. SI unit of power is diopter, right? D we represent. Suppose, okay, diopter it is also called per meter. Diopter it is also called per meter, right or not? Okay, diopter per meter. It is also we say per meter, right? Okay, now so for focal length of we know it. Focal length of convex lens is positive, no? Focal length of convex lens is positive, no? As power is equals to 1 by f, no? Focal length of convex lens is positive. If positive, then therefore power for convex lens is also what? If this is positive for convex lens, power for convex lens will be positive. In the same way, for concave, power will be negative because focal length of that will be what? Focal length of concave lens is negative, therefore power of concave lens will be negative. Got my point? Okay, this is regarding what? Your lens, right or not? Right? Okay, now after learning this, then we'll go to the MCQs, right? Directly we switch on to MCQs regarding concave mirror, convex mirror, plane mirror, and then lens. Okay. Now let me move to the, okay. Now let me move here for uh, your object MCQs. Done? Okay. Now be ready with MCQ now. Be ready with the notebook and pen. Now we'll solve some MCQs. Okay. Right? Okay. Now let's see once again. Okay. Now, so let me take out this first. Okay. Now let me move on for the first question. Two vertical plane mirrors. Two vertical plane mirrors. Two vertical is 60 degree. 60 degree with each other. A ray of light traveling horizontally is reflected first from one mirror and then from the other mirror. So actually we have got two plane mirrors. What is the angle between them? They clearly put 60 degree. They are asking what is the total deviation after reflection from both. You already know it. What is the deviation after reflection through two? It will be just it is independent of angle of incidence. Deviation will be what? 2 theta. It's an angle of incidence independent of angle of incidence. What is the deviation? It will be 2 theta. Therefore, deviation is equals to 2. What is the theta? Is the angle between the two plane mirrors. What is theta here? Angle between the two plane mirrors. It is 60 degree. What is answer here? 120 degree. But we don't have options in the answer. See, 120 degree, I told you already, 120 degree, there are two possibilities. If this is incident ray and this is, suppose somewhere it is a deviated ray, final ray. If one way, if it is a 120 degree, the other way it has been, we can mention deviate how much? 240 degree. All both possibilities are there. If one way it has deviated by, suppose it may take here, it is anti-clockwise. Suppose it is an anti-clockwise. If it is deviated 120 degree, possibility other way also you can say no, it has deviated by an Angle of 240 degree in clockwise. Anyhow, direction is mentioned, not mentioned here. 60 degree, 180 degree, 30 degree, 240 degree. Then okay, I'll go with 240 degree. That's also possible here. We have got 120 degree with this formula, no problem. So 120 degrees in one sense. The other angle possible was 240 degree. It will be in other sense. Got my point? So I'll go with fourth option. Okay, now next. Here, what should be the angle between the two plane mirrors so that whatever be the angle of incidence, the incident ray and the reflected ray from the two mirrors should be parallel. Actually, what is given is actually two mirrors are like that. What the question is, whatever may be angle of incidence here on the one mirror 1 or mirror 2. Important is if this is incident ray after reflection from the both, they told here the incident ray and the reflected ray from the two mirror parallel. Now it is the incident ray, it's a reflected ray. Are they parallel? To happen this parallel, what should be the angle between the mirrors? Right or not? Okay, again let me use the formula deviation is equal to 2 theta. Deviation is equals to 2 theta. Right or not? So deviation now, let me, if both should be parallel, if one incident ray is coming like that, another ray is going like that, both are anti-parallel, no? So it means both are deviated through 180 degree, no? If your deviation should come 180 degree, okay or not? Your deviation should come 180 degree, then ultimately theta will be what here? Is it theta? Theta will be 90 degree here. Got my point? So if deviation should be 180 degree, your theta should be what? 90 degree. Got my point? So which option is correct for you? This. Okay. Now, okay, next let me go for the next one now. So next thing here is a ray of light incident on plane mirror of angle of plane mirror, ray of light incident on the plane mirror at an angle of what? 30 degree. Then the deviation produced in the ray. For single plane mirror, what is the deviation formula? 180 degree minus 2i. 180 degree minus 2i. So deviation produced by single plane mirror is 180 minus 2. What is the angle of incidence here? 30 degree. They given already. Let this be 30 degree. Therefore, it will be what? 180 degree minus 60 degree. Is it what? 120 degree deviation we are getting? 120 degree. So D option is correct. Right? Okay. Next one. When a plane mirror is rotated through an angle theta, then the reflected ray turns through an angle 2 theta. Then the size of the image is. So remember, if this is the mirror, if this is the incident ray and this is a reflected ray, if suppose your mirror turns through an angle of theta, your reflected ray will turns through an angle of 2 theta. I already learnt it. Here, if reflected ray is here, what image is you are getting here? What is the size of image and all the same, the same reflected ray comes here, same image we are getting, no problem. Complete rays shifts here, size will remain same. What size you are getting here, the same size you are getting here. If you turn the mirror through some angle, it doesn't affect the size of the image, it will remain same, no problem, right or not? So size will become, it remains the same, size becomes okay, it remains same, size will remain same. Okay, now next move on to a plane mirror produces magnification of, what is the formula for magnification? Minus V by U. So plane mirror for real object, it will produce virtual image, no? So for plane mirror, you know it already. If object is here, image is somewhere here. V will be positive, U is negative, U is negative, V is positive, U is negative. Right or not? So one thing is there, we can say distance of image and distance of objects are same, and so minus here V is positive and U is negative, minus into minus plus, and then this same UV equal to U. What you are getting magnification? Distance of image equal to distance of object. Got my point? So therefore, I'll say here the magnification of plane mirror will be 1. Done? Magnification of plane mirror is what? Magnification of plane mirror will be 1. Done? Okay. Now, let me move on to next one. Okay. A small object is placed 10 centimeter in front of a plane mirror. 10 centimeter in front of a plane mirror. Okay, here we have plane mirror. A small object placed 10 centimeter. Somewhere here object is placed. How much distance away object is placed here? How much distance away object is placed? 10 centimeter in front of the plane mirror. If you stand behind the object 30 meter from the, okay, somewhere a person is standing. How much distance away from the mirror? 30 centimeter away from the mirror. A person is standing where? Here is a person is standing. A person is standing here 30 centimeter away from the mirror. And look at its image. The distance focused for your eyes will be. Okay, this person to see this image. Okay, now very clear. If object is 10 centimeter in front of the mirror, image will also be. This is somewhere the image 10 centimeter only. 10 centimeter only. Right or not? Then observer will observe this image. At what distance that image will be there? Here to here already 30 and this is 10. 40 centimeter away he will focus the eye, to see the image of that object, this particular object. Here to here the mirror to object is 10. The mirror to image will also be 10. The person is how much distance from the mirror? 30. So here to here 30, the image he has to focus here. Then 30 plus 10 will be what? So distance focused for your eye will be at what distance he is focusing? 40 centimeter from his place. Right or not? Okay. From 40 centimeter from his place. Right or not? Okay. Now, next. See here, an object is at a distance of 0.5 meter in front of the plane mirror. Okay. Let me say here plane mirror. This is a plane mirror. Where is the object here? Somewhere here object. At what distance that object is? 0.5 meter. 0.5 meter in front of the plane mirror. The distance between the object and the image is, okay, if object is here, image will be here. This is image. The object distance and image distance will be equal, no? Here this is also 0.5. Right or not? What is the distance between object and image overall? Is it 1 meter? Here to here 0.5, here to here 0.5. Is it 1 meter? So what is the distance between object and image? 1 meter, right? 1 meter. Am I right? Is it okay? It will be what? 1 meter. 1 meter is the answer. Okay. Now, done. Let me take the next one. Okay. The light reflected by a plane mirror may form real image. Suppose this is the plane mirror. When this will form real image? Sorry. Usually for real object case, it will be what? Virtual image. But their case one, if suppose rays are hitting the mirror in converging fashion, in which fashion now these rays are hitting? Converging rays are hitting. Converging rays are hitting. So where they supposed to meet at? They supposed to meet at here. But they finally meet somewhere here. After reflection, they meet here. Somewhere they meet here. They retrace, and this is image here. This image is real. This image is real. When that real image forms, if the type of rays hitting the plane mirror, if it is converging type, then the image nature in the type of image there we are getting is real image. Got my point? Okay, then which option? If the rays incident on the mirror are diverging, if the rays incident on the mirror are converging, this is the answer. If the rays incident on the mirror are converging. Got my point? Okay, now a man having height 6 meter, he observes image 2 meter. Okay, image height here is what? 2 meter. Man height, object height is what? 6 meter. And the image is erect. Which type of image we are getting? Erect. where you are getting? You have already learnt in case of convex mirror, size of image will be always less than the object. Size of image is less than and it is always erect. Size of image less than the object and then it is always erect. So which case it is possible? That is convex. Which kind of mirror where it is possible? Convex mirror. Got my point? So that's possible in case of convex mirror. Okay. Now, focal length of plane mirror is, okay, you know it for mirror purpose. What is the focal length is R by 2. This is a relation for plane mirrors. Okay. For plane mirror, R is infinity. For plane mirror, R is infinity. Then definitely focal length is also what? Infinity. Therefore, the focal length is also infinity. Got my point? Okay. Now, today we'll close, and in the next class, tomorrow, we solve some objectives on the lens and on concave and convex mirror. So today we close it. In the next class, we'll solve some more on MCQs. Then we switch on to magnetic effect of electric. Done? Thank you. Okay.